I think we can start. Our first speaker of this session is Giacomo Tendas from Masarykova Univerzita, and the title of the talk is Flatness, weakly-lex colimits, and reactive completions.
Thank you, Enrico. Thank you all for coming, and thanks for having me, the organizers, to the scientific meeting. So today, as Enrico said, I'm going to talk about reactive completions, in particular of weakly-lex categories. So the aim is my aim was to understand the free exact completion, the universal property of this free exact completion, in a more formal way that I will try to explain to you later, which is captured in the context of lex colimits introduced by Gardner and Lack. And to do so, we see that we'll have to introduce a notion of flatness that generalizes the standard one that maybe you know about. Okay, so maybe let's start saying something about the more standard exact completions. And for now, when I say exact, I mean bar exact. So if you want an exact category is one with finite limits, which from now on we call it lex, which has, in addition, co-equalizers of equivalence relations, which are stable under two. And people have talked about them also during the conference, so I'm not going to say much about exact categories themselves, but mostly about the free exact completion of a lex category. And you can see it here. It was introduced by Carboni Manuel. And it's defined by this universal property. So given a lex category C, so a category with finite limits, the free exact completion Cx is given by an embedding of C into Cx, is an exact category and satisfies this property. So left-hand extending of K induces an equivalence between lex functors out of C and exact functors out of Cx, where the target category is any exact category. Okay, and Carboni and Manuel already showed that Cx can be obtained by C just by freely adding co-equalizers of the C equivalence relations, which are generalization of co-equalizers of equivalence relations. You just somehow dropped the uniqueness condition when defining an equivalence. Alternatively, Cx is contained in C offset, but you can also see it as the closure of C of the representables under finite limits and co-equalizers of equivalence relations. So this point of view, if you want, is more formal because you just use the structure, not the structure, but the limits and colimits involved in the exactness conditions, so finite limits and co-equalizers of equivalence relations. But the first one, maybe it's more useful because, well, you just do a one-step thing. You just take co-equalizers of C equivalence relations, while the second one is closer. However, the second one is very formal, and in fact, it can be captured more generally in the setting of 5 lex colimits, which, as I said, were introduced by Gardner and Lack. So I'm not going to define them in general. Just think about a class 5 of colimits. Think of them as those colimits to which you impose your exactness conditions. In the previous case, they were co-equalizers of equivalence relations. But could be co-products in the case of extensive categories, could be co-equalizers of kernel pairs in the case of regular categories, and so on. In this setting, you have a notion of phi exactness, and you can define the free phi exact completion, just mimicking what we had before. So given a lex category C, the free exact completion phi of C satisfies the universal property, as shown there, with the only difference from before that we have phi exact factors out of phi of C. So those factors that preserve finite limits, and in addition these phi lex colimits that I told you. And as before, this phi of C can be obtained by closing the representable in C offset under finite limits and these new colimits. So exactly as before. And these are some examples that I've already mentioned, also pre-Topley. But the thing that I want to mention today is that this doesn't seem to capture a free exact completion that is actually very common, it appears very commonly, and is the free exact completion of a weakly-lex category, which I'm going to talk about. So what's a weakly-lex category? It's a lex category. It wants to be a lex category, but you don't have all the limits as they are usually known. So a weak limit of a diagram is an object together with a code, but the universal property is weakened by by dropping the uniqueness condition in the factorization with respect to arguments. So I say that a category is weakly-lex if it has this kind of limits, which of course are not unique up to isomorphism. You can have different weak limits for the same time. Okay, but then Carboni and Vitale shows that if you start with a category which has only weak finite limits and you freely add coequalizers of pseudo-equivalence relations, as we did before, this is still an exact category, even if C is not lex. And moreover, it satisfies a universal property, which is the one I'm pointing out here. So on the right-hand side, you still have the exact factors out of Cx into any exact factor E. But on the left-hand side, you can't have lex factors because, well, C is not lex. So you have to replace them with something else, and that's what Carboni and Vitale did. So what are these called? Which are the left covering factors. Okay, so here is the definition. F is a left covering factor, remember, out of a weakly-lex C. If for any finite diagram, and then a weak limit of that diagram, if you take the image of the weak limit and compare it to the actual limit of the image of the diagram, because E is lex, or in this case it's actually exact. So you can take the actual limit. You want a comparison mark to be a regular. And if you take this kind of factors, you obtain the universal property I've shown before. And this means in some sense that F preserves the weak limits. So F of C will still be a weak limit, but it's actually a stronger condition.
Excuse me, why did the reference
I think, I'm not an expert of the story, I think they introduced them independently at the same time. So also who, in one of his papers, introduced the notion of left covering factor. Yes. Thanks, because I should have mentioned. Okay, so that's the notion. If C is lex, then any left covering factors and lex factors are the same. And if E is set, then they are the same as the flat things. And that will be important later. But my question here was, this is very nice and actual and practical, but how did they find out that this was the notion? How did it arise? Why is this the natural thing to consider? And what's actually a more formal definition which involves maybe preservation of limits or colimits? Let's try this. Okay, so that's my motivation. How can I find a more formal approach to this, and which maybe lives. So my approach, I wanted to live in the context of 5 lex colimits, so that I can apply the theory and get even more examples. And I should say at this point that first Karatzeris and then Schulman already took over this question and introduced a notion which captures left covering factors in a formal way, but they define them for factors between categories with topologies. I didn't want to do that. I wanted something which doesn't rely on some additional structure. Okay, so looking at this, the idea at the beginning was, well, should be something that generalized flatness. to the context where the target category is not that of sets. So let's see that. Okay, so well, let's take a functor into set from any small category, C. That's commonly called flat if its category of elements is filled. But there are many different ways of defining flatness. And the others involve the left-hand extension along Uneda. So you have C to C offset, and you take the left-hand extension of F. And equivalently, F is flat if this left-hand extension preserves finite limits. But again, this is not the exact result I want. The exact result that I want is the third one, which is saying that to have flatness is actually enough to consider the preservation of finite limits of representables. So we don't need to go all the way to consider all the finite limits here. Spoiler. Okay, so I'm going to start mimicking this definition by replacing set with any lex category E. Okay, having in mind that the left-hand extension along Uneda doesn't exist in general. Okay, so I can't do just this. I need to somehow replace it using the pointwise definition of the left-hand extension. So first of all, on the right-hand side, we clearly have the limit of the image of any finite diagonal into C, so limit of FH. So to define flatness, let's take the left-hand side, and since this might not be defined, let's simply say what's the colimit that defines the left-hand extension, which is this one. So it's taken along the capital elements of the limits of y applied to h. So I have h into c, we can apply to Uneda. And that fortunately has a simple enough description, which is the category of cones over h in C. Okay, so that's the definition that works. I say that a functor from C to E is flat if for any diagram, finite diagram H from D to C, this colimit exists and is isomorphic to the limit in the target category, which exists because I'm assuming that E exists. Okay, so let's check the first few properties. If E is set, by definition, we recover the usual notion of flatness. If C is lex, as it was in the case of leftover functors, flatness and being lex are the same. And if the target is a gradually topos, then we kind of recover the third property here, that the left-hand extension preserves finite limit of representables, but even more, all finite limits. Okay, so now that I have a notion of flatness, I can go back to the setting of phi x colimits and define what does it mean to be a phi x completion of any small category. I just take my notion of flatness and put it on the left-hand side. So sorry? Yeah, that's right. I meant the notion of flatness that I just introduced coincides with the original one. Sorry about that. Okay. So we can introduce this notion of free phi exact completion for any small category C. I can define phi L of C as before, as the closure of C under finite limits and phi x colimits, and say that that is the free phi exact completion on C if left-hand extending induces this equivalence. And since flatness in the lex case coincides with being lex, in that when C is lex, this is just the free phi exact completions that we had before. However, at some point we'll recapture the theory, the weakly-lex word, but already that says that the free file exact completion doesn't always exist, so this property is not always true. For the weakly-lex case, you need C to be weakly-lex, but in general, for example, if you take phi to be empty, you already need to be C to be lex itself. So the first thing we need is actually a theorem that tells us when does this exist, when is this property satisfied. And this is a bit technical, but so I won't go into the details, but just say a few things. So to characterize when the free phi exact completion exists, I introduce this full subcategory free sheaves, which you should think as start from the representables and add all the kind of colimits that exist in a phi exact category. Colimits taken along flat factors that exist in a phi exact category. So think about the exact case, so bar exact categories. Then phi diamond of C, I'm adding co-equalizers of pseudo-equivalence range. Okay, so that's the idea of phi diamond. Then the theorem says that C has the free phi exact completion if and only if this phi diamond is equal to this, the phi L that I've just introduced before, and if and only if this phi diamond of C actually has finite limits of diagrams of landing in C. Again, the idea is that in the exact case, finite limits of diagrams landing in C are exactly weak limits. So if we apply this theorem in the exact case, we just get back the usual theorem saying that by equilibrium that the free, regular, and exact completion of a category exists if and only if it is weakly-lex. And moreover, we can do what I wanted to do, which is characterize left-covering factors as those flat factors that I have introduced. I've repeated the definition. And now I will show you some other examples. Using again this theorem, I will take some examples of phi, and using the equivalence 1 and 3, I will tell you when some free phi exact completions exist in relation with respect to the existence of some kind of weak limits in your category. So, for example, if we take the class phi for infinitarian extensive categories, so that have small coprolus and this satisfies some exactness conditions like being some stability under callbacks and having the empty intersection. Then the existence of the free infinitarian extensive completion is equivalent to C having finite multilimits, which is a notion introduced by Thiers a long time ago. And what's a multilimit of a diagram? It's a family of objects together with cones, and then in the universal property you require that the factorization exists uniquely, but with respect to a unique index I in the family, and then it is also unique with respect to the cone delta I that we chose. Then we can do the same, well, in this case, flatness corresponds to the notion of finitely multi-continuous factor. So it's a factor that sends a multilimit like this to this. So the co-product of the element, of the image of the elements of your multilimits are actually the limits of the image. Then you also have the finitary case, so just extensive categories with respect to finite co-products. And it's just the same, just the only thing that changes is that instead of multi-limits, you have these that I'm calling multi-finite limits, since I didn't find any reference to them in the literature. If you know of a better name, do tell me. The difference with multi-limits is just that now your family needs to be finite. It's not anymore an infinite family. And again, flatness is characterized in the same way. Then you have a similar result for pre-topoi, so exact and extensive categories together. And the notion of limit that you get in this case is somehow put together multi-limits and weak limits, and so you get a finite family where now the factorization is not unique, not in the index and not in the actual factorization. And now flatness, again, can be characterized this way, which kind of reminds you about the left covariant functors, but here on the left-hand side you are doing some compromise as well. Another interesting example is if you take phi to be kind of described colimits of free two-point actions, then the free phi exact completion in this case exists even if your category C has finite polylimits. They are like multi-limits, but now the factorization is unique up to an automorphism of your object. And such free phi exact completion are called quasi-based in a thing of Pointoli. And I didn't have enough space to tell you what's a polynomial functor. And finally, if you take a sound class, think about finite limits, and you take the D-filtered diagonals, filter about D-filtered colimits, then you also get a result in this case by saying that C has a free phi exact completion, even though the free completion of C under D-filtered colimits has finite limits of diagonal elements. And I think this is all I wanted to say.
Questions or comments?
Hi, thanks for the talk. Can you comment on the connection between these phi exactness properties and Rosenberg's topologies on the category?
If I have a comment. Actually, I haven't understood really the relationship, because in that setting, the notion of flatness that you get, it depends on making a choice on your two categories C and P, which is the topologies you want to consider, right? I don't make any, so I'm actually don't know what to say in that regard. It's something that I still need to check, but I tried a little bit and didn't see a very close relationship.
Giacomo, thank you very much. I had a question similar to that of Josh, but I have a comment. And I think that it's, I think go to one of the first pages when you mentioned Californian manual.
Yeah.
Because I've noticed recently that she is referred to incorrectly. And if you don't mind, I take this opportunity to correct, because her surname is Celiarano, and her name is Roberta. And she's then Roberta.
So it's not a good name of the surname.
And she is now a retired teacher in mathematics. I can't remember where around Milan, but I think that Celiarano should be always used as a surname.
I will use it, yes.
Thank you very much.
Yes, may I comment on Bepe's question? Because I'm not sure actually. When you mentioned two references, yes, I think Aurelio was insisting. Monica is here. Aurelio was insisting on not using Giordetta, and who was using Giordetta? Is it correct?
Yes, in fact, it is the main difference between the paper by two and paper by variance. More questions or comments? If not, I have one. And well, I know that the regulator categories are a strange kind of animal. But I wonder if your point of view could help to understand homological functor from a triangulated category to an abelian one, because they look very much like a left coordinate functor, so maybe it should be so it's not a question.
It's something that maybe we'll have to look into. Yeah, I cannot say anything right now, but maybe, yeah.
So, thank you again.